Alright, let's get started on the percent composition activity. So our goal today is to determine how you can calculate percent composition by mass of elements in a compound. Alright, so let's start with a basic example of pizza. This is a great classic example that anyone can take a look at in order to really think about what percent composition really is. So, example, if we have 8 slices of pizza, and that's a whole pan, right? And you eat 4 slices, what percent of the pizza do you eat? Well, any logical Chem 1 student would say 50%, because we all know 4 out of 8 is 50% of the pizza. So, how exactly did we get that number? If we think about it, all we did was 4 slices that you ate divided by the 8 total slices times 100. So, we can take that, method of calculation and calculate percent composition as well, where we take the part value divided by the whole times 100. Let's try some examples and apply this to some chemistry practice problems. Question 1 says you were very hungry after practice and ate 5 slices of the pizza pictured above. We have 8 total slices. Alright, 8 total slices in the pizza given. Alright, so if we ate 5, that's part 8 whole times 100. Right? You go ahead and plug that all into your calculator. So 5 divided by 8 gives us 0.625 times 100, which is 62.5%. So what percent of the pizza you ate? You ate 62.5%. Question 2 says your friend didn't have practice after school, so she wasn't hungry and ate only 2.5 slices. Well, same deal here. We're calculating what percent of the pizza she ate. So 2.5 over 8 times 100. 2.5 over 8 is 0.3125 times 100 gives us 31.25% of the pizza she ate. Alright, moving on to the next question here. You fed the dog the rest. Probably not a wise choice, but what percent did the dog eat? Right? So we have 8 total slices, and we already gave away 2.5 in question 2, and we ate 5 slices. Alright, that gives us a remaining pizza count of 0.5. All we do is take that 0.5 over 8 times 100, which in the end will give us 6.25% of the pizza remaining, which was given to the dog. Alright, your mom was also hungry, and so you ordered 2 pizzas. If she ate 43.75% of the other pizza, how many slices did she have? This one's a little more complicated because you have to actually use your brain and think about the algebraic way of solving this. I believe that my Chem 1 students can all do this calculation, but I'll walk you through. Let's start with the percent value. We know that in order to get the percent value from these fractions, we have to multiply it by 100. So let's cancel that out first. 43.75 divided by 100 gives us 0.4375. And we know from our previous calculations that a whole pan of pizza is 8 slices. Let's make a note to that side. 1 whole pizza equals 8 slices. Alright, so let's set a function up, right? 0.4375 equals some part number pizza over the total 8 slices in a pan. Therefore, if we multiply 8 on both sides to cancel the x, or 8 on the denominator of the x over 8, we can solidify our x value as a total value of 3.5. And therefore, in order to eat 43.75% of the pizza, you need to have 3.5 slices of pizza. Alright, not so hard. Alright, skipping on and moving forward, ignoring the experiment, the bubblegum experiment, which you will do in your labs in class. Let's take a look at how to calculate percent composition for mass of compounds. Alright, not much different here. Let's think about this. So it gives us percent composition by mass is part of a whole times 100. We just did this part, so we understand that part over whole means that if we have 5 out of 8 slices, that basically just becomes 5 over 8 times that 100 for the percentage at the end. But for compounds and molecules, it's a little different, because if you think about it, what makes up the mass of a compound? Say we have water, let's write here H2O, right? That's a very famous chemical or compound. That's water, right? So if we think about the mass of the compound, your mind should immediately kind of jump around. Let's think about the mass, molar mass on the periodic table. So if we want to determine the mass of the compound, we would either be one, given it, or two, we'd have to find it. And in this case, we would try and solve using molar mass of water. Molar mass of water is 18.02 grams per mole, which is the units for molar mass. And we would know that the mass of the element would be the molar mass of whatever element that we want to find. So if you wanted to find the molar mass of hydrogen, there's 2 hydrogens. 2 times 1.01, which is the molar mass of hydrogen. And we have 2 of these, so we have to multiply it by 2. Vice versa, if we wanted to find it for oxygen, we know that it's around 16, and we'd only multiply it by 1, because we only have 1 oxygen element in our water compound. And so by doing this, all we're doing is taking the specific molar mass of the element you just want to find over the total molar mass of the compound. And we'll see that on our next page here. Alright, let's ignore all this fancy stuff all top and just take a look at what we just talked about right here. The molar mass of sodium in sodium chloride, NaCl. Excuse me. So, in order to find just the molar mass of or percent composition of sodium as a mass value, we just take the molar mass of sodium over the total molar mass of sodium chloride. Then we'll just have a percentage value after multiplying by 100. Using this information, let's go ahead and try some practice questions. So, question 1 says, when 19.0 grams of a compound containing only iron and oxygen is decomposed, 5.7 grams of oxygen is released. What is the percent composition of oxygen and iron in the compound? Alright, so let's think about what this question is asking for. Well, we know that we got to find percent composition. And this is the first time we're going to be using this special little molar mass equation. So let's try to think about what this iron and oxygen thing is really talking about. Iron is Fe, and so we don't know these numbers. So it's some compound that looks like this, where X is X some number and Y is Y some number, right? But in this case, we can pretend we don't see this. That's just for visual aid. And so in reality, what we need to do is think about what 5.7 grams of oxygen released means. And so if 5.7 grams of oxygen is released, it means there was 5.7 grams of oxygen in the compound in the first place. Now, knowing that, that's our part value, because the compound is composed of both iron and oxygen, but we were just given 5.7 grams of oxygen that was released. Therefore, we would take that number as our part, and for our denominator, the whole value, we would try to put the mass of the total compound, which is 19.0 grams. So 19.0. And what do we have to do for percentage? We have to add that times 100 at the end. And therefore, if we plug this into our calculator, we will get 0.3 times 100, which is 30% oxygen. And now it wants percent composition of both oxygen and iron. So let's think about this for a bit. And if percent is based off 100 and 30% is oxygen, then logically what we have to do to calculate iron is 100% minus 30, which gives us 70% iron in the compound. And therefore, this is your final answer. Alright, let's now talk about the percent composition of each element in some compound named NaHSO3. Right, at first this seems a little intimidating, like what in the world is NaHSO3? I've never even heard of it. But in reality, it's very similar to question 1, except instead of just iron and oxygen, this time we have 4 elements: sodium, Na, hydrogen, H, sulfur, S, and oxygen, O. So instead of having 2 atoms, like FeO, we're going to have 4, and that's just more work for you. There's nothing more difficult about it. And so in order to solve these questions, we always need the part value and the whole value. But if we look at the question, it wants everything, the percent composition for each element. Therefore, we do need the whole value for all of them. So let's calculate that. In order to calculate the whole value, you just got to find the molar mass. And so the molar mass is found on your periodic table. It's that big number underneath the 2 or 1 letter alphabet name of the element. Sodium has a molar mass value of 22.99. Hydrogen has a value of 1.01. Sulfur has a value of 32.06. And oxygen, we have 3 of them, so multiply by 3. 3 times oxygen's molar mass value is 16. Therefore, our total sum, we just got to plug into our calculator. And in the end, that should theoretically give us 104.06 grams per mole. Remember, grams per mole is the unit for molar mass. And now we have all this information and we can just use it and plug it into this format and solve, right? It's just repetitive multiplication and division, right? So let's take a look at our first one, sodium. I like to go in order. Let's label this sodium. We have 22.99 over the total value 104.06, and we have to multiply that by 100, which will give us in the end 22.09% sodium. Alright. And next, take a look at hydrogen. 1.01 over 104.06 times 100, which will give us, if you plug into your calculator, 0.97% hydrogen. And remember, I'm rounding this to the nearest hundredths place, just for your reference. And S, sulfur, excuse me, sulfur, we take 32.06 over 104.06 times 100, which gives us, here, let's separate this here, which gives us a value of 30.81% sulfur. And finally, for oxygen, we have 16 times 3, which is 48. Let's make that parentheses first. 48 over 104.06 times 100, which should give us a percentage of 46.13% oxygen. Alright, and so there is all your percent composition for sodium, hydrogen, sulfur, and oxygen in the compound NaHSO3. Alright, number 3, calculate the percent composition of each element in CH3OH. Alright, another one that looks super complicated, but it's literally the same thing as 2, except we only have 3 elements to work with: C, H, and O. And so a key thing to note here that is we have H in 2 different spots, right? So we have to take into account that there's actually 4 hydrogen atoms, not 3, because there's 3 separated here and 1 here. So when we calculate our molar mass, which we need for all of these percent composition questions, as seen in question 2, we're going to calculate the value of hydrogen for a total of 4 times instead of 3. Just make sure you don't leave out 1. So 1 of carbon, which is 12.01, plus 4 times 1.01, which is the value for a single hydrogen, times 4. And then you add that with oxygen, which is just 1 oxygen atom, so it's only 16, which gives us a total molar mass value of 32.05 grams per mole, and that is the unit for molar mass, don't forget. And now to calculate percent composition, all you got to do is find the individual molar masses. So we already done that, right? And it's simple, right? So carbon, 12.01 part over whole, 32.0, that looks like a 7, 32.05 times 100, which should give us 37.47% carbon. Next, hydrogen, we have 4, so 4 times 1.01 is 4.04, 32.05 underneath. Let's make that a little neater, which should give us a percentage of 12.61% hydrogen. Alright, and lastly, oxygen, we got to take 16 over 32.05 times 100, which should give us a value of 49.92% oxygen. That's horrible looking too. Percent oxygen. That's it. Double your percents. Alright, moving on to, let's see here, if I can scroll up. Calculate the percent composition of each element in C6H12O6. Same deal with the previous questions. It's just, repetitive. Yeah. So let's calculate the molar mass of that. This time we have 6 of the carbon. Each carbon's 12.01 grams per mole based on your periodic table. Plus 12. Each hydrogen is 1.01. Plus 6 oxygen. Each oxygen 16 times 6. All right. And you plug this all into your calculator. And you get 180.18. Here, 180. Where's my marker? 0.18 grams per mole. All right, and that's going to be your whole value. Percent composition. We have 3 atoms, which means 3% composition we need to find. Start with carbon. Carbon, 6 times 12.01, which is, let's see, 72.06. Carbon, 72.06 over part over whole, so 180.18 times 100, which gives us 39.99% carbon. All right, so H, we have 12 times 1.01, which is 12.12 over, oh, that looks like a multiplication, 12.12 over 180.18 times 100, which will give us 6.73% hydrogen. Oxygen will give us 6 times 16, which is 96, over 180.18 times 100, which will give us around 53.28. All right, so that's a all 3. Oh, that looks horrible. All right, that's all 3% compositions found. And if you're ever unsure of your answers, well, all the percents have to add up to 100, right? You're not just randomly losing like percents of elements in like a percent composition question. So just add all these up. See if they match 100. If it does, you're good. If it doesn't, well, either you probably did some rounding wrong or you're completely wrong. So, I mean, it'll be pretty obvious, because if you're like 99.39, right, that probably is a rounding question. But if you're like 83.1, right, then clearly you've done your math wrong. So that's an easy way to check whether or not you've done it correctly. Question 5 says you have an unknown compound that contains carbon, hydrogen, and oxygen, and using analysis, yada yada yada, the compound has 53.3 oxygen. That's the most important part there. What compound do you have? CH3OH or C6H12O6? You're probably thinking, well, I don't want to do all that percent composition crap again, right? Well, luckily, the questions 3 and 4 have been building up for that. You found all the percent composition of CH3OH in question 3. And you found all of the C6H12O6 in question 4. All right, and the question 3, if we flip back here, the percent of oxygen, let's highlight that in yellow here, was 49.92. Remember that, because we're going to write it here. All right, 49.92%. Versus question 4, well, we just found that, right? It's on the top of right corner of your screen here, 53.28. So then which one's closer to 53, right? Obviously 53.28. Therefore, which compound do I have? Well, question 4 was talking about C6H12O6. Let's go ahead and circle that in green here. C6H12O6. Therefore, the question molecule in question, the compound in question, is C6H12. Let's write that a little better. C6H12O6. Alrighty. What's the percent composition of each element in aluminum nitrate? The question says, right? And so let's calculate, as with all percent compositions, the total molar mass for our whole value, where we do part over whole times 100. Aluminum nitrate, let's think back to our nomenclature unit. Aluminum has a +3 charge, and nitrate has an NO3 1- charge. So we need 3 nitrates for 1 aluminum. Therefore, our compound name is AlNO3, 3. Alrighty, so with that information, let's go ahead and calculate our molar mass. Total molar mass is going to be Al molar mass, which is 26.98 plus, let's see, nitrogen. Remember that when we have this, it means you just multiply. So nitrogen has that invisible 1 after it. So 1 times 3 will be 3, obviously. So 3 times the molar mass of nitrogen, which is 14.01, plus 3 times 3 here is 9. So 9 times the molar mass of oxygen, which is 16. Add all that together, and you will get 213.01 grams per mole. Alright, that looks a little weird. Someone just write grams per mole on the side just a little bit. That's our total molar mass value. Thinking about percent composition, well, same thing. We've literally done this like 5 times. It's the exact same process, unless the question decides to be mean and like you see something like 7, which we'll talk about in a little bit. Alright, so percent composition. So let's start with aluminum. When I look at these chemical names, I always just look at these and just go with whatever order they're in. So I'm going to go aluminum first, nitrogen, oxygen, but you can go whatever's convenient for you, as long as you don't forget one and you're just not equal to 100% in the end. So aluminum molar mass we found was 26.98 over 213.01. That's a horrible parentheses, but pretend that is nice. And times 100, which gives us around 12.67%. Alright, and we have aluminum here. Horrible square once again. Alright. N. We have N, which is 14.01, and we have 3. So 3 times 14.01 gives us 42.03 over 213.01 times 100, which gives us 19.73. Alright, and that's good. And in theoretics, we can just subtract this all from 100, but let's go ahead and do this all for the question's sake. 9, so we have 9 oxygens times 16, which will give us 144 over 213.01 times 100, which if you plug into your calculator gives us 67.60% oxygen. And there we are. That's all add up to 100, aluminum nitrate, all atoms, aluminum, nitrogen, and oxygen accounted for, and therefore that is your final answer. Alright, let's take a look at question 7. So how many grams of nitrogen are contained in 36.5 grams of aluminum nitrate? And from our previous question, let's go ahead and recall that aluminum nitrate, AlNO3, 3, so horrible 3, okay, that's another bad 3, okay, why is it doing that? 3, is equal to 213.01 0.01 grams per mole for its molar mass. We calculated that in our question above. Here, why don't I just move up a little so you can see the previous question. And so if we read the question, it's asking for grams of nitrogen from the 36.5 sample of AlNO3 aluminum nitrate we have. And so at first you're like, what in the world am I supposed to do? But if you really think about it, all we got to do is find how much of aluminum nitrate is nitrogen, which we found in the previous question. 19.73% of the compound AlNO3 is nitrogen. All we got to do is just find what 19.73% of 36.5 is, right? So let's just think about that. Just take a step back and really think about what that means. So we calculated in the previous question that out of one AlNO3 compound, 19.73% is nitrogen. Of this is nitrogen. Alright, and based on this information, if we have 36.5 grams of it, all we have to do is multiply the percent value in decimal of the 19.73% of it, and that will give us the grams of nitrogen, right? Since AlNO3 has 19.73% of nitrogen in it, then if we have 36.5, it's the same thing. 19.73% of it is going to be the gram value of nitrogen. So let's take this 36.5, and remember, 19.73% really is 0.1973, right? All we got to do is divide by 100 if we have a percent, and we'll get the decimal version of that, right? And so in order to determine what percent of in order to determine what 19.73% of 36.5 grams is, just multiply it, right? 0.1973 times 36.5. And if you multiply these numbers together, you're going to get 7.2. That's it. 7.2 grams of nitrogen is going to be your final answer, right? Out of 36.5 grams, 19.73% of it is 7.2. Therefore, your final answer is 7.2 grams of nitrogen in the 36.5 gram sample. Alright, and that is it.